Welcome to our new webinar series on quality assurance and process optimization for additive manufacturing and the role of computed tomography. My name is Gabriele Meurer and I'm Regional Sales Manager at Yxlon. We're very pleased that participants from more than 20 countries have joined in today. With this webinar series, we want to bring insight into various aspects of additive manufacturing or 3D printing. For that, we have invited specialists from the community who are involved in research or industrial applications. Our webinar series is divided into individual webinars, which will take place at different dates and times, and each session is focusing on one specific industry, technology, and application. Today, we will have a closer look at an aerospace application. And I am very pleased to welcome Dr. Elena Lopez from Fraunhofer IWS Dresden. Elena is the head of division additive manufacturing and has been working in the field for more than 10 years. She holds a PhD from Technical University Dresden and has been the author of numerous publications on different technologies for additive manufacturing. And she is the ambassador of the Women in 3D Printing program that seeks to increase the visibility of women working on additive manufacturing technologies. Dr. Lopez will introduce an aerospike rocket engine which was designed and produced at Fraunhofer IWS. Due to its unusual design, it can save up to 30% fuel compared to conventional rocket engines. Dr. Lopez will share her ideas on the conception of this part and how they managed to produce it with laser powder bed fusion. She will also explain how non-destructive testing NCT has contributed to the evolvement of this part. And now, I will hand over the word to Dr. Elena Lopez. The floor is yours.
Thank you very much, Gabriele, for the nice introduction, and welcome everybody to this workshop concerning developments for CT and aerospike additive manufacturing rocket engines. I would like to share my presentation so that we can proceed with the first slides. So the talk of my presentation, as mentioned, is additively manufactured rocket engine with aerospike nozzle, and a special focus will be set today on the role of post-processing and non-destructive testing. I would like to thank also especially the PhD candidates Samira Gruber and Michael Müller involved in these developments, as they carried out most of the experimental and technical work of this project. Our story concerning the development of the additive manufactured aerospike rocket engine is quite long already, as it can be said that we started with first design approaches at the beginning of 2016. And then by using the advantages of processing with additive manufacturing technologies, we were able to optimize the geometry of the different aerospikes involved until we had that 2019 a hot gas test at the setup of the Technical University Dresden to prove the functionality of this part. At the moment, we are working in 2021 on the further improvement of the aerospike nozzle itself. As you may know, conventional rocket engines are based of a combustion chamber and a Laval nozzle, and the fuel gas used, which can be one fuel gas or a mixture of different fuels, gets burned. And during the expansion of the gases in the Laval nozzle, the sufficient thrust for the movement of the engine and of the satellites or rocket which is being moved can proceed with the movement. In the case of the aerospike, the components are slightly different. We don't have combustion chamber, but a ring or annular combustion chamber and an aerospike nozzle with a special geometry. In the with the label nozzle, we have or we are in deep correlation with the atmosphere conditions, the atmosphere pressures, and the design pressure of for the Laval nozzle must be adapted to the environment pressure. That means it's not so flexible to work with this kind of nozzles. Looking to the aerospike, we have the advantage that the aerospike nozzle is not being so influenced by the outside conditions, and the efficiency at different altitudes, for instance, is higher than the one obtained for a conventional combustion chamber. That means we can achieve up to 30% higher efficiencies done with the conventional manufactured nozzles. You see also in the picture on the right side that's the burning. These are infrared pictures of the different burning processes depending on the attitude. That we have different representations of the burning process, but the efficiency is always being kept quite high. Moving to the advantages of the aerospike, we can see that apart from this special design that cannot be made with conventional manufacturing, working with additive, we can spare mass, we can be independent of the ambient pressure, and that's why we get 30% less of fuel consumption. We can print smaller nozzles with less weight, and in the end have a possibility also to inject a second combustion gas to have the possibility of use a direct thrust vector to direct the engine to the wanted direction, let's say. So it is a wide world of possibilities that can be used by additive manufacturing that cannot be made by conventional manufacturing. By the way, I think I didn't say it before, but this design of aerospike rocket engines is already available since the years 1960s, but it was not feasible for the aerospace engineers to make it possible before due to the fact that the reasonable and interesting manufacturing technologies were not there on the market. So the conventional manufacturing didn't make possible to have these complex geometries you have seen with cooling channels, with special channels for the also flowing of the fuel. So this is really an application that was waiting to be put into the market until the appropriate technology arrive. So concerning the appropriate technology, I mentioned already, it's going to be made by additive manufacturing. That's where our institute comes into place, into the scene. We work at the Additive Manufacturing Center Dresden with a wide range of technologies in the field of additive manufacturing, from printing with, sorry, this is the printing with polymers up to nozzle technologies for laser cladding. And finally, technologies like the one we used here, powder bed fusion technologies, where using powder and depositing it layer by layer, very complex geometries can be made exactly like the ones needed in the case of the aerospike. So we took advantage of this available process chain at IWS, and also, as it's going to be mentioned later on, the characterization by means of non-destructive testing, in this case computer tomography, was a very relevant point, and it was a real advantage that we had an excellent system to carry out non-destructive testing and be much faster with the process development than without using computer tomography. So I've mentioned some of the advantages before of the aerospike. They are summarized here on this slide. The interesting point probably is to see on the right side of your screen a video showing a picture of or a video of a computer tomography where you can see the spike building up. I think I will come back so that all of you can see it from the very beginning. This is the aerospike from the very beginning with the cooling channels, yeah, the configuration all over the aerospike. At some point, we will see the combustion chamber, the annular combustion chamber, with also the periodical inputs for the fuel on the outside. We see also the support structures during the powder bed technology in the middle that help to avoid distortion or to have a really good buildup of the part. And in the end, you see, yeah, the final part or the final geometry of the aerospike. So we use this computer tomography from the one side to compare actual nominal geometries from the ones designed from the space engineers to see that we have no defects on the part to avoid porosity and cracking, let's say. But also to see, yeah, if there is maybe any problem concerning powder rest on the cooling channels, to see if the surface structure is the one that we wanted. So I will comment that later on, because we also need to have a good surface quality to enhance the effectivity or efficiency of the engine. And that's why CT was really a very helpful tool for us. So, sorry, from the conceptual design to the tested part, I would like to go now on the different steps that we carried out to have a functioning aerospike engine. So mostly in our design, the aerospike consisted of two parts: the chamber, the combustion chamber, and the spike with injector, as you can see on the top. We designed it for a thrust of 500 newtons so that we can test it also on the hot gas measurement setup at the Technical University in Dresden. They were our partners there. And we have internal water cooling of the spike with the combustion and the combustion chamber. The developments of the process chain were, we needed to optimize, let's say, the parameters for laser powder bed fusion, which is, yeah, it requires some time, definitely. And then for the machining, post-processing, the laser welding of the parts, and obviously also for the additive manufacturing and the process quality management. So the quite fortunate step is that we have all technologies at AWS to assure high quality all over the process chain. So we have the raw material characterization, additive manufacturing, heat treatment to get the high temperature properties of Inconel 718, mechanical post-processing, joining of the main combustion chamber to the aerospike, and then finally also the non-destructive testing. So coming to the point concerning the material, I mentioned we use Inconel 718 because we have very high temperatures up to 2400 Kelvin during combustion conditions. And it is well known that these alloys are able to work at high temperature regimes. Obviously, we need some heat treatment to activate the relevant gamma phase that is important for these high temperature properties. And that's why we moved to this additive manufacturing build-up with laser powder bed fusion, as you can see in the image. We use a Renishaw AM400 machine. And what we try to do, obviously, is to see which are the minimum wall thicknesses that we can print, the minimum channel diameters, the obtained surface roughness, and the distortion. Because if we have higher distortion, we would need to do something also later on with the post-processing. I mentioned before that Inconel 718, as mentioned, is it's material that is well known to be used under high temperature regimes. And as I mentioned before, we can be lucky to have maybe temperatures up to 2400, but these properties are not available just after printing. We need to, let's say, make them by using a heat treatment so that we have the wanted gamma phase due to this aging in the oven. Later on, we will need to have a machining of the parts to have a good aerodynamic condition of the surfaces. And then we had also to join these two parts from the additive manufacturing processes to the final aerospike engine. So one of the interesting points was that at Fraunhofer IWS we have also the access to the technology laser beam welding, just to join this aerospike nozzle up to the combustion chamber, localized with a really a small heat input on the surface, and also to avoid more distortion. That would be not really definitely a good point then at this level. So once this has been done, then we move to the non-destructive testing with Epsilon E535CT, which is available at our lab. And we saw that the possibility to work, I mean, Inconel 718 is also well known for a high absorption for X-ray, and the resolution needs to be also, let's say, needs to be investigated to get a very well resolution under certain CT parameters. So what we saw in the end is that we had the resolution up to 20 micrometers for this material, which is sufficient, let's say, for the application. And we were looking, as said before, for cleanliness, cracking, available pores, etc., that could lead in the end to a malfunctioning of this engine in the space, which is would be a critical mistake in the during the testing, to have one of these levels. And then I mentioned before, powder in cavities can be an issue and also lead to significant damage. So CT was really a great tool to see that we can manufacture these parts and get rid of powder included from the process. So from the geometrical prototype I mentioned at the beginning, 2016, we moved to the functional prototype, which needs to be tested, obviously. That was the plan, at least at the, let's say, installations of our partners. And this is it. That's what you can see here, with the two parts made up for the testing. And I will show you more also concerning the testing of this already functional part, or functional ending. We use the capabilities of the Technical University and the Institute for Space Technology, and work with two different fuels, as a liquid oxygen and ethanol, with mass flows up to 500 grams per second, sorry. And what we wanted to see if the engine is able to work in a proper modus with within a combustion time of 10 to 20 seconds. So this is not a really huge test under application conditions, but just a test to see if everything is fine and is working, which is already a huge step in the use of this engine. The whole process has been monitored with infrared cameras to see if the thrust and this is the one as expected for the atmosphere conditions, and to see also if there is any problem with the fuel, with the gas injection, and so on. And everything was at this point satisfactory so that we can declare this test as a successful test for the use of aerospike in space applications so far. So what we have been also trying to improve during all of these research projects concerning the aerospike is also the post-processing improvement concerning machining for the outer surfaces, but also abrasive flow machining concerning the inline channels for cooling and for the gas fuel. One of the possibilities also of the aerospike is not only to cool with water, but to use the fuel and let it flow also as a cooling medium, so that you would have two effects. You would get rest heat from the high temperatures in the engine, but also can preheat your combustion gas and spare energy at the end of the day to have a more efficient engine and less cost, let's say. So what we wanted to do is, by terms of abrasive flow machining, also to optimize the surface of the water cooling and gas cooling channels to have the best efficient as possible. And you may know probably abrasive flow machining requires abrasive medium. There is obviously a chance that some rest of this medium stays there. And we wanted to see by non-destructive testing if the abrasive flow didn't lead to any contamination of the surface, and in the end to a detrimental effect on the aerospike engine. Then the heat treatment is also a science itself, as it can be yeah, researched in a very deep way to get the most out of these material properties. And then finally, also to avoid Inconel, to get to higher temperatures that it is reasonable to work with. We decided also to cover some parts of this aerospike with thermal barrier coatings made by thermal spraying with a base of yttrium materials, so that we have a better heat management within the walls of this engine. So research question on abrasive flow machining and CT scanning are, for instance, what is the minimal diameter that can be post-processed? Obviously, constrictions and limits. And we wanted to see what's possible. That's why we use the CT for that. And what we did, as you can see it on the back, or let's say on the right side of the slide, is a CT scan before abrasive flow machining, a comparison with the first scan with the CT file, a second CT scan after the abrasive flow machining, and then comparison of this first and second scan to see also what's the minimal diameter feasible without contamination, without maybe irregular faces or irregular surfaces that can lead to a bad functioning of the engine. We also experience in this way how much material is removed depending on the material, sorry, on the channel geometry. So you can calculate it quite easily also from the weight, from the volume and density of the material. And then the roughness, it was a good question for us. We can measure the roughness using a CT. Obviously, with a tactile measurement, you can measure the roughness of some parts, flat parts and so on, but the inner cooling chambers were really a challenge for us because they are not accessible. So it could be a great input if we can see that the roughness can be measured by CT. So that's why we tried this, to have a measurement of the roughness. And the procedure we follow was to have a classical CT scan. Obviously, it took some time as we are working with Inconels 1.8. Then we use probably if you are familiar with CT, known steps concerning surface determination, fitting of the geometry. In this case, it is a cylindrical geometry. So you see, we did special channels. We printed special channels, but not the whole spike part. And then destruction of the region of interest with VG Studio to see if we can find out more about the surface. Further on, we had the cylindrical unwrapping, extraction of square surfaces, an application of a Gaussian ill filter, and the separation into waviness and roughness. And before I just finish with the conclusions, the nice message was that, as you can see it also from the pictures on the right side, it is feasible to get information about the roughness of the surface for inner walls of cylindrical geometries. And this was for us definitely a milestone that was achieved for the further development of the aerospike technology. So interesting also maybe for you to know what's the which are the next steps for this development. Obviously, this is not the end. We invested some resources with the Technical University Dresden to put this aerospike into life at the beginning of 2016, but it also gave the fruits that we obtained 2 different projects to work on further developments on this. One of them is funded by the Ministry of Education and Research here in Germany, and the project Agent 3D. And here the focus is mostly based on the optimization of the injection heads for aerospike engines. You can imagine that there is still a lot of music behind the design of the spikes themselves. And in this exactly approach, we are focusing on that with partners like Siemens and the Institute for Material Technology at the Technical University Dresden, also the Institute of Aerospace Engineering, who were there with us also from the very beginning of this development. And then the second project really closer to an application or to a flight into space is a European Space Agency project called Spira, where we are testing with the ESA and with other partners like Ariane Group or the Institute of Aviation in Poland, really flights with these machines. So not just hot gas testing, but really the possibility to explore how it feels like to have a real space flight on the atmosphere outside in the space with this kind of development. So this is the plan for the next couple of months and years. So I hope if you're interested in this research, you will hear more about that. And yeah, that's it from my side. Thank you for your attention, and I'm happy to answer questions or comments if you have any after these slides. Thank you.
Thank you, Elena. Thank you very much for sharing these insights with us. And we have several questions here. I will read them to you, and hopefully you can answer them. The first question is regarding the material. You mentioned Inconel 718, which I believe is a difficult material for NDT. The question here was, does the tube have enough power to penetrate this material, or are there any difficulties?
Mm-hmm. Yeah, this is a great question, especially for our seminar today, because yeah, there were difficulties. As I mentioned before, so we work quite usually with this kind of nickel superalloys in additive manufacturing due to the very good mechanical properties, high temperature properties, and low weight. But obviously, also we have discovered in the past that yeah, they have a higher absorption behavior for X-ray radiation. So I remember that it was crucial for this development that we have this, or we have this great collaboration with Ixilon in Hamburg. And to measure the whole first geometrical prototype, it was necessary to move to the installations in Hamburg. So I remember we were able to measure some mechanical samples, some cylinders, as you have seen with our EV35 CT, but fortunately, due to this great collaboration and the easy contact to the installations in Ypsilon, we could access higher powers with the CT. And yeah, you have seen the video. So definitely, yes, it is feasible to measure inconel, but you need high power CT and you need the experts like Ypsilon, for instance, that tell you exactly or maybe suggest you which CT is the most suitable to spare time.
Okay, thank you. The next question is regarding the size of the defects. You mentioned in your presentation that the defect can have 20 micrometer and you could detect that with CT. The question here is there a limit for the size? Or how do you decide when to reject the part and when to keep it?
Mm-hmm. That's a good question. The limit to this 20 micrometers was set by the material that we have. Usually the roughness that we need for this application is around 15 to 25 microns. So it's fine in the level that we achieve. But for some critical parts, maybe some bendings of the cooling channels and so on, there is nothing left than maybe making a special sample and use a destructive testing for this special critical part. But in this case, where we knew, okay, this level of resolution of the CT is exactly in the level that we want, then everything is fine. But I agree that for additive manufacturing and other applications, it might be critical to measure other defects, and obviously you would have also, you can go down to a better resolution also with CT and other materials. Then I know the specialist also from Ypsilon can confirm this. If you work with titanium, with aluminum, polymers and so on, you can go much farther down with the resolution, and probably you would have the enough resolution for your application. If not, there are cases obviously where you would need to check maybe during the process optimization, not really during the whole time, but just during the first critical time of process optimization with some destructive testing.
Okay, thank you. One question is, how large is the part? On the photograph, it looks like about 25 centimeters. Is that correct?
We had different sizes. I mentioned we had this geometry prototype, and we have this functional prototype for the heat or for the hot gas testing. The prototype for the hot gas testing was smaller. The biggest was around 25, right, centimeters, and the hot gas prototype is definitely smaller than that. If I remember right, around 20, but I can also, if the person interested really wants to know exactly the dimensions, I can just refer to the PhD colleagues working on exactly on that to send the exact dimensions if this is of interest.
Yeah. Okay. Our next question. How do you remove leftover powder from those inside channels?
So we work with this abrasive flow machining, where you have a fluid. I had some slides on that, but probably was too fast. You have a fluid with some solids, abrasive particles, let's say, inside, and we can administrate this fluid. This is a suspension actually through the cooling channels, through the fuel channels, and just due to this abrasive interaction with the surface, we have the possibility of getting rid of this powder. Obviously, is this a question of optimization? That's why we used CT to see if we had enough abrasive effect on the surfaces. But that was the way to go. In German, maybe if it's interesting for a German-speaking participant, is Stromungsschleifmaschine.
Okay. Next question. You showed in your presentation that the aerospike consists of two parts. Why was it built out of two parts and then welded together instead of making one part?
This was done to get a better surface roughness of the inner part of the combustion chamber. That means we use this machining, as you have seen probably that we also use mechanical machining, but not only abrasive flow machining. And we noticed that it's more beneficial to have these two parts to get the surface roughness required for the combustion chamber, which has no, actually in the outside, no special features. And then just combine the aerospike with the aerospike nozzles with the combustion chamber in a quite fast step of laser beam welding. And we have these technologies all one hand at IWS, and that's why that was for us the faster and technological, more time-sparing process chain, let's say. We didn't investigate to print it. I mean, it's feasible to print it in one step, but probably also the machining, you can use abrasive flow machining for the combustion chamber walls, but probably this would require, this is too much, no? A little bit too much to get that surface in the necessary quality.
Okay. Speaking of a roughness surface, here's a question. How do you determine the uncertainty of the surface roughness measurement?
This is something that I cannot I cannot answer myself because I was not doing the CT experiments. But if the person interested, just drop an email to my email address or whatever about the Ixilon colleagues. I will let you know I would put you in contact with our CT specialists. I don't know if somebody from Ixilon can also answer this question because it is software related from the city software, but yeah, due to the fact that I don't work directly on the city, I cannot answer that.
I think it was related with roughness, precision. Maybe there is no no validation for that, and whether there is another technology to verify that. But we need to check that later on. I also don't have an answer right now.
Obviously, there is, in our measurements, as we use CT for the surface roughness, definitely there is an uncertainty as in any measurement. But yeah, I cannot provide the value exactly as I was not directly involved in the measurements. I can give it afterwards. Just drop me an email.
Here we have a question regarding crack sizes and again, the resolution. How big were the smallest crack sizes and how were the smallest flaw sizes verified?
We could go down to 20 microns. So that was the smallest crack that was just measured for this value. And obviously during the first trials or the first process optimization, we needed also to check or we got a better resolution with smaller parts. That means we also check let's say porosities in a less level, in some microns level that are feasible to be measured with the computer tomograph. And once we had our optimized process parameters, we knew that we can get rid of the smaller defects and then just focus on the higher defects for the whole part. And yeah, it was confirmed then by the real test on the hot gas setup that yeah, we were right with the assumption that there were not critical mistakes anymore or defects.
Here, somebody wants to know regarding the process. Have you applied HIP, hot isostatic press, for this part?
Yes, we
Yes,
use it as
very
well.
clear. Okay. Another question, do you use the powder again? Meaning, I understand maybe regarding recycling, right?
Mm-hmm. This is also a great question. So for this project or projects, we didn't do it so far. As we were really producing, you can imagine we are the lab, so it's really not a huge amount of aerospike engines that are there, but obviously this is an important question as far as it gets to production. And we have some projects running on that, on using reconditioned powder for certain applications, or maybe also sometimes low budget powder for certain applications. And so if you follow certain steps, for some alloys, it's feasible to use it again, but also depends on the safety required for your final application. So for aerospike engine, it would need to be tested definitely. It was not so far because we didn't have the focus on that. But it would be also a great research topic to see if we can use, because Inconel has high technology material and high expensive material, let's say, and it would make sense to use it from the powder bed again.
Okay. Another question here. Do you have any design for inspection tips applicable to CT scanning of rocket engines? What if the material is copper alloy?
Copper alloys. I don't know if I understand the question clearly. I mean, I see it here. Okay. Do you have any design for inspection tips applicable to CT scanning or your analysis? What if the material? I mean, copper alloy. So we have definitely also projects on copper alloy, and there are also companies like Pangea in Barcelona and Spain, 3D printing aerospike engines based on copper due to the very good thermal conductivity properties of copper, ductility and so on. And so we have also a focus on copper, for instance, for aerospike applications, for e-mobility, for instance, heat exchangers and so on. So we work also with copper at IWS, also in the aerospike sector. A throwback maybe right now for copper is that the conventional green laser machines at the moment are just 100 millimeters in diameter and height, and we can print just very small aero spike engines. So the technology, these Trumpf machines need to get a little bit bigger to get a reasonable size, but it could be feasible. I have also the impression from or feedback from our colleagues on CT that copper is also easier to work with than Inconel on CT. And yeah, concerning tips and so on, yeah, we have definitely these design tips. And we have also, depending on the material, on the wall thickness and the application, different procedures for this.
Okay. Next question regarding the technology and the process again. How do you perform thermal barrier coating to the inside of the part?
Yeah, the thermal barrier coatings were made also before joining, laser beam joining the parts. So it is easier to achieve the relevant surface. And this was done also at our institute by means of thermal spraying. So again, just one-step solution, so it was relatively easy for us to get that tested. And we did this definitely before joining the parts, so there is no constraint on the geometry then after that.
Okay. He wants somebody to know how long you scanned and the number of scans. Do you have that information available, or is that something we have to?
No, it's something because especially for instance, for the video, no, this was made in Hamburg. I would need to check also with your colleagues. I don't know if Niels was involved on these measurements or not, but this is something I can provide afterwards because I don't have these numbers in my daily business. Sorry for that. I think, yeah, I don't know if Ixlon had any experience right now from the feeling working with Inconel. I wouldn't assume working with a higher power of the source. I would guess this is feasible in some hours of scanning to get the best resolution. But yeah, if you want to comment on that, Gabi or Niels, you're welcome.
Yeah, that is something maybe we take, we discuss after the session. I don't have the values here with me right now. So how can you detect unmelted powder in the printed material with the CT volumes?
Yeah, this is we can. And this was also a question that we had, or a constraint, worry about the non-melting powder. And we saw also those phenomena, and yeah, could get rid of that with the abrasive flow machine in the end. But this is something that happens. You need to take it into consideration, definitely.
Okay. And how long is the printing time?
The printing
PDF.
time for the biggest engine was 48 hours, everything together. So the different parts.
And are the aerospikes for sale? If so, what do they cost?
That's a nice question. Obviously, as Fraunhofer Institute, we are not really producers. Now we are a non-profit organization working on applied research, and are happy to collaborate in research projects to have any improvement on the technological development of those engines. So we can collaborate in research projects by different ways, direct collaboration with industry or European or local funded project, but we don't really sell finally developed parts. So this is the common Fraunhofer way is to bring something to application, and then that's why you have seen some companies on the projects as well. A company takes care of that at some point when the part is already optimized, and then put it in the market now, because that's not really a Fraunhofer thing. But yeah, so they are not really to be bought by Fraunhofer. Maybe, yeah, if the person is interested, can drop me an email as well, and I can put you in contact with the companies involved in the project, so maybe they can give you an indication if they're going to sell these components, or when they are going to sell these components, or which is the plan. Maybe they are able to sell some prototype or something like that.
Okay, thank you. We have several more questions related to the size of cracks and so on, but this is really something we have to check later on. So for those who are interested, I recommend you to send us email, and we will get in touch with you and discuss with you directly on these specifics. I think you have our contact details in the emails which we send out, or you can contact us via LinkedIn, Elena, myself, my other colleagues from Ixlon. I would like to thank you very much all of you, Elena, and my colleagues who have participated in this webinar, and also you as a visitor, as our guest. I want to let you know that we have our next webinar already lined up, which will take place in 4 weeks from now on the 22nd of June at 2 p.m. German time. And this time we will focus on ceramics and the direct ink writing technology. So we also have invited an inspiring speaker again, and we'll hear presentations and have a discussion later on. All the details on this new webinar you can find in an email which will soon be sent out to you, and you can register for the new webinar then. So save the date, and I hope to see you there, and see you soon. Bye.